Thank you. Well, thanks to LSU, for the Math Department, for inviting Susan and me here. We will talk for 2 weeks on twisted Alexander invariance. And today, I really just want to do some classical things, just to remind or maybe inform some of you about what the classical theory is like, and 3 ways of looking at classical Alexander invariance, Alexander polynomials. It's important for a couple of reasons. One is so we know how the twisted theory really is a twisted theory, but also because it motivates a lot of open questions. First, at the outset, let me say there's an embarrassingly large amount of things that are not known about twisted Alexander polynomials. It's almost silly. Things that analogous statements for the classical invariants that have been known, since Alexander. And so maybe this will motivate it. It will also give a chance to get some terminology, notation sorted out. And that seems to be a real big problem with the subject, because if you've been looking at some of the papers, they're all over the place with the notation. So we're going to try to be as consistent as possible and try to capture as much of an average notation as we can with the theory. So let me begin by really basic notation. Throughout this talk, through these talks, K will always be a knot, usually an S3. We'll be looking at some knots and homology spheres later. X, so this is a knot, of course. X will be the exterior. So this is S3 minus the neighborhood of the knot, and then take the closure. So we get a compact manifold, exterior. And of course, the boundary of X is the torus. We're also going to just call the knot group pi. So that'll be true for 2 weeks. Pi is just the fundamental group of X. The knot group abelionizes to Z because the knot is a homology circle. And so the most natural homomorphism to apply to pi is something that we'll call epsilon. This is really an abelionization. And we'll think about the infinite cyclic group as generated by T. No relations. So this is the abelionization. So the kernel of this is the commutator subgroup, and we'll call that pi prime. This is the kernel of epsilon. And now we have a first place where notation is going to become upsetting. We want to look at the universal abelian cover, the covering space with fundamental group equal to the commutator subgroup. But we want to reserve tilde for the universal cover. So throughout we'll call this thing X prime, which is reasonable because it matches the commutator subgroup. So this is the universal abelian cover. X, fundamental group, of course, is pi prime. Also throughout R is going to be a Noetherian unique factorization domain. For a lot of situations, we're just going to be looking at the integers, but also fields and sometimes more exotic things. So the first comment is that let's see, I guess I should go over here. Is that if we look at the first homology of the universal abelian cover, and do it with Noetherian, with R coefficients, then this is a finitely generated module over the ring lambda, it's a bit more notation, of Laurent polynomials with coefficients in R. And let me just say that the subject can be very algebraic, and it can also be more combinatorial and diagrammatic. And we're going to kind of move back and forth between these 2 points of view. So if you're not as comfortable with some of the algebra, just wait a bit and it will change. Not like the weather here. Okay, so hey, I'm from Mobile. I know about this weather. All right, so this is a finitely generated module, and since this is a Noetherian, then this is a Noetherian module. So hence Noetherian. All right, so first there's a very classical lemma. Can you see this, or should I be seeing it? Okay. First is that if we have the action of t, you should be thinking about t as deck transformation. I'll try to show you some pictures soon. You should be thinking about t as shifting you along the infinite sigma cover, which has, of course, the deck transformation group is just generated by t. So think about t as shifting you. And the first result is that if you look at the homology with R coefficients, and you look at the action induced by t minus 1, with the homomorphism induced by t minus 1, so just shift by t and then subtract what you shifted, that this is surjective. This stuff will break down when we get to the twisted case, and so that's one of the reasons why I'm mentioning it now, and it's one of the things that makes twisted homology not only sometimes annoying, but also very interesting when you get to things like detecting when a knot is fiber and that sort of thing. So this is going to break down. This is going to be actually very interesting later. Okay, so let me just say a word about the proof without going into great detail, because it's a very pretty proof. And this holds in some will hold in some twisted cases, and so will the proof, and that's another reason to look at it, but it doesn't always. So there's a short exact sequence of chain complexes. Where we have the chains on the universal abelian cover, and then t minus 1 acts on that the way it does in homology, and we have the same chain complex. But the quotient, if you're going to identify t times a chain with the chain, then all you're doing is taking the universal abelian cover and just folding it back down and just getting the original complex of x. So if we take the quotient of this by the image of this, then this is just the chains on x. And this is a short exact sequence. So if we have a short exact sequence of chain complex, that induces a long exact sequence of homology. And a long exact sequence of homology looks like this, and this is the part of it we want. H1 of x prime with coefficients in R, t minus 1, H1 x prime in R, H1 xr, H0 prime of R, H0 x prime of R. And let's see, these three are all simply R. This one, because this is just the ordinary homology of the knot complement, and knot complements are homology circles. So this is just really, you think of the abelianization of pi 1 tensored with R. This is just R. X prime is a connected space, so this is just the zero homology. And again, zero homology. Now, if you've got, you can think of t minus 1 is just going to, t is just going to be the identity on R. And so t minus 1 is going to be 0. This is going to be the 0. This is going to be the 0 homomorphism. So now you just have to trace this back, and in particular, it's going to imply that that's 0. Just have to chase it back a little bit. And that tells you that this thing is surjective. Okay. So again, let me say something that's going to happen in the twisted case. This isn't going to be so any longer. And actually, even figuring out what the zero twisted homology is in some cases can be tricky. This also isn't going to be true, of course. Okay.
I have a question.
Please.
Universal Boolean color, is that the same or different from the infinite color?
Same.
Okay, so it's just different actually.
Yeah. And please feel free to ask that kind of question. One reason we're setting up this language also is that we're not going to do a lot with links, but a lot of this theory goes over very beautifully for links. And so if this becomes a link in several variables, I mean several component link, then this is again the group. This is still the abelianization, but now this is z to the variable, mu or something, yeah, and universal abelian covers what you want to use. Okay, right? So I'm going to toss out problems and exercise. This is more like a homework exercise, just for students. But homework, maybe there'll be a difference between homework problems and open problems. This is not open. Show that t minus 1 is also injective using the Noetherian property. And you have everything you need to do it. It's a nice exercise. Let's see, I'm told only to use these two things. Oh, yeah. It's okay. So the important corollary here is that H1 of X prime R is lambda torsion. It's a lambda torsion module. And risk of completely putting the cognoscenti to sleep here. Cognizant of the students in the room. Let me give a very brief sketch of the proof, because I think the proof is very pretty. And by the way, if you want a reference for some of this stuff, I guess I should have said at the outset. We'll try to give references for each of the lectures. A really good reference for a lot of this stuff, including this argument, can be found in Gordon's survey paper, Some Aspects of Classical Knot Theory, which is in a survey which is in a collection of lecture notes and mathematics. I think it's 695. I think
it's actually available online. I can try to get a link to it. They can get it online.
I did something I don't usually do now with PDF files and all that stuff. Is I actually brought paper copies of some stuff. So if we need to make a photocopy of this, then we can do it.
But it is online.
The survey is online. Nice.
Recent.
Who put it there?
Springer.
Oh, very good. Thank you. Do you need to pay the money?
Well, your friendly LSU library has to pay the money.
Well, I'd like to get a copy of that so I don't have to drag this thing around. All right. Right. There's no reason to drag any papers around. So here's the idea. Assume A1 up to AN generated on page 1 of the prime coefficients in R. And we're not assuming that this is a basis in any sense. We're just assuming that they're generators. So since it's corollary, right? So we're supposed to be using something here. Since t minus 1 is surjective, then that means we can write any AI as t minus 1 times something, a word in the A1 through AM, because the A1 through AM generate. So let's just write down something, summation, j equals 1 to m, lambda, ij, aj. So for some m by j, lambda. Again, it's because t minus 1 is surjective, so everything's got this form. And now we just bring the AI over. And so what this means is that summation j equals 1 to m. Now I'm going to change the lambda ij's. Sometimes we'll get a 1 subtracted from them, and sometimes they won't. Well, let's see. I'm going to write. Right. So this is mu ij. Aj is 0. And so if you want something very specific, the mu ij is t minus 1 lambda ij. If I isn't j, and it's t minus 1 lambda ij minus 1. If I pull this j out, just solve. Okay? So the interesting thing is the matrix mu ij. And the aij's are a solution, essentially, to this matrix. And so if we let delta be the determinant of mu ij, then delta ai is 0 for all I. Because we have a solution. So in particular, that means delta is an element that annihilates the homology. But of course we have to make sure that delta isn't what? Could be 0. That's cheating. So we have to make sure that this thing really is something. And the way we do that is a cute trick. If we look at let's say it this way. Consider the E is evaluation. We're going to map lambda to R by sending t to 1. Okay. Then since E of mu ij, so look at the form of mu ij here, since t is going to go to 1, this is going to vanish under E, and this will go to minus 1. Yeah? So this thing is equal to minus chronic delta ij. Let me see why we actually wanted to write down this form. So, therefore, E evaluated on delta has got to be close to minus 1. The matrix evaluates down to just a bunch of minus 1s down the diagonal. Yeah. And so therefore, delta is not. Oh, I said, excuse me, I shouldn't be using delta. I switched my notation because I didn't want you to think that delta was the Alexander polynomial. Well, it's very close to, it could be the Alexander polynomial. The problem here is that the AIs are just generators. But in fact, the Alexander polynomial will have to be lurking in here. Classical Alexander polynomial has got to be a factor here. So here we're just trying to get the fact that this is kosher. Once you've got a torsion module, now there's a whole standard theory of elementary ideals, determinants that give you the classical Alexander Polynomial. And I don't want to belabor this, but let me just mention the notation that we use here. So since lambda is a unique factorization domain, there exists a sequence of elementary ideals, call them EI, and characteristic polynomials, or elementary divisors. There's a lot of different names for this. I like to call them characteristic polynomials, but elementary divisors is another term, delta I. And they're defined in a very simple way. So this matrix will be used a lot. We'll do a twisted version soon. That's another reason to mention this notation now. Let M be the M by N presentation matrix. For the homology, the universal even cover with entries in lambda. Because we have a finally generated module. And just to keep your numbers straight, N here correspond to generators on top and into each row. And these are our relators.
So we have some exact sequence between three groups, and the image is the homology, and M is the matrix that describes the first map.
Yeah. You can think about the AIs as generators up here, and we know that we have some relations that we can put in, and we'll only find a number of relations because of the Noetherian property T, which you've got a fun presentation. We can always add extra relators. We can always at least get this thing to be a square. We might have to a priori add more. So you can always say at least then that without loss of generality, that M is bigger than or equal to N. In other words, this thing is at least as deep as it is void. And so EI is going to be the ideal generated by determinants of minors of a certain size. So this is the ideal of lambda generated by all, and the index here is n minus I plus 1 times n minus I plus 1 minors, or subdeterminants. So let's see how that's going to work. When I is equal to 1, when I is equal to 1, you just go down until you get a square matrix. Take the determinant. Okay. So E1 is simply the ideal generated by a single determinant. In that case, that's going to be the one that we're most interested in, because we're often going to have a square matrix. But
well, you have to get rid of one row, but
yeah, did I not do that?
Yeah.
Let's see. No, we're okay.
Well, you're just saying you're only going to get one determinant, but you're supposed to look at all of the n by n determinants.
Oh, sorry, that's right. Yeah, what I mumbled is that if we have a square matrix.
Oh, if you have a square
Yes, thank you. If we have a square matrix, then we just have to look at one determinant. Yes, if you have more relations, then obviously you can look at all the possible n by n, for sure. And then you go on. You can look at the next smaller size determinants, and that will give you the ideal of 2. And then you can look at the next smaller size, and that will give you the determinant.
And is the idea that if you just have one determinant, then of course course it's principal, but if you have more than one determinant, then maybe it is, maybe it isn't.
Yes, that's right. At least if you're working over something like C, which is often the case, quite right. Okay, so let's see, and we're gonna just put EI equal to lambda if you run out of stuff. All right, so since so here's the way you get the polynomials. Since lambda is a unique factorization domain, EI is contained in a unique minimal principal ideal, which denoted by ideal generated by something delta I, a unique smallest principal ideal. And delta I is called the ith Alexander Polynomial. Okay, and it's well defined. This is an important fact. Well defined up to multiplication by units. By units in lambda. Now, what is a unit in lambda going to look like? Well, it's going to look like a unit in R, t to the plus or minus, or t to the I for some R, where R is a unit in R. So, in the case of Z, for example, this would just be plus or minus t to the I. To recap, the classical Alexander polynomial is well defined up to plus or minus t to the I. When we get to the twisted Alexander polynomial, there'll be things that we can do to eliminate some of the indeterminacy. There are actually things we can do to eliminate some of this indeterminacy for the classical case. They're well known, and I'll say something about the Alexander Conway polynomial, for example. There's ways to normalize to get rid of some of this indeterminacy. So the elementary ideals nest, obviously, and the Alexander polynomials divide each other. So we have E1 contained in E2, etc. And that means delta 1 is contained in delta 2, etc. And so therefore, delta I plus 1 divides delta I. And if you get I big enough, then delta I is just 1. Because EI is lambda. That's how it works. So, a little bit like what we saw in that argument before, showing that that element delta that annihilates the homology is non-trivial, we can actually see that, that these delta i's are non-zero. We have a torsion module, and in fact they have a nice augmentation property. So we're going to move on. Since t minus 1 acting on a homology is surjective, what it means is that if you look at the homology of the universal abelian cover, it's a lambda module, but if we think about it as an R module, where R acts on this thing by first killing T, sending T equal to 1. And so in other words, where R acts via E, or I should say, by lambda R, by killing 1, by killing T, sending T to 1, then this says that that this thing is 0. This thing vanishes. And hence, these elementary ideals evaluate are just R. And evaluate this way. And so the just evaluating the ith Alexander polynomial at 1 should give us a unit. This is equal to delta I. So all these Alexander polynomials have the property that when you evaluate them at 1, you get a unit. So if you're working over Z, if you evaluate an ith Alexander polynomial, you get plus or minus 1. So unless otherwise specified, we'll assume, at least for today, that R is Z. Unless otherwise specified, just for now. And in a survey paper, Gordon makes a comment that I've always thought was really kind of a provocative comment. He said the Alexander polynomial is essentially rational invariant. And what he meant by that is that if you tensor, if you let R be a field, if you let it be the rational numbers, and you do all this, all the algebra becomes very nice because lambda, which is QTT inverse, is a PID. The whole theory of PIDs. And so you can write you can write this homology as a direct sum of cyclic modules, collect the factors at the bottom, and reconstruct the Alexander polynomial by simply multiplying by appropriate integer in order to normalize and get back integer polynomials. I think I want to. What time do we start?
5 after.
5 after. I think I'd like to let me just say a word about that, and then try to get to some concrete, straightforward examples. A lot of this is to set up some notation and terminology and mention what algebra is true for the untwisted case. But computing these things is actually very easy, at least for reasonable sizes. So let me just mention what Gordon said about the Alexander polynomial. It's essentially a rational invariant. I don't know, it's not maybe not that original comment, but let me just mention what it means. So let R be Q, lambda is QTT inverse, is a PID, and hence the homology, the universal Wheeling cover breaks up as a bunch of cyclic things, R, where the Fi are non-zero. Why is it non-zero? Because this is torsion. So being non-zero is equivalent to this module being torsion. So we know that it's non-zero and well-defined up to units. Then delta 1. Oh, I didn't say that delta 1, the first Alexander polynomial, is written delta. Drop the I, drop the 1. Delta 1, since it's the one most commonly used, is sometimes written delta. And if we want to indicate the dependence on the norm, we might put it. So delta 1, delta, is the product of these FRs. And moreover, this is a nice comment. You can get back if you're working over the integers, you can get back the integer polynomial by just multiplying through to clear the denominators, and only clear the denominators. Make sure that the coefficients are relatively prime. And you can get back the classical Alexander polynomial. But there's something about this that I didn't want to skip. So let me say this because this is such a nice way to think about it. H1 of a homology of the universal Wheeling cover now is a finite dimensional vector space. Vector dimension, the degree of the Alexander polynomial. And in fact, the Alexander polynomial is the characteristic polynomial of T, multiplication by T.
What does degree mean here? It's only defined up to T to some power.
Well, that's a good question. Normalize it so that the you can talk about it as the span, the largest degree minus the smallest. Or even better, when you do the normalization, make sure that you've got a non-zero constant term and no negative exponents. Yeah, thank you. So the point is that delta is the characteristic polynomial of the automorphism of T. Or to say it another way, delta 1 is a comparison of two bases. I mean, in some ways, that's what characteristic polynomial do. It's comparing the basis and the translated basis by T. A lot of invariants in knot theory come about by comparing two bases. I mean, those are familiar with the Brow representation in braid theory. There's a comparison of two bases. We'll say something a little later about how the twisted Alexander polynomial is actually twisted right much toward it, and that comes about by comparing bases. So from that point of view, it's maybe not as mysterious. It's just a vector space automorphism, just looking at the characters of the polynomial. So let me make this a little concrete and show you the fastest way I know to compute Alexander polynomials. Because really what you want to do now is compute a few of them. And that's the second bit of homework. So, well, let's start with the trinomial. Show you how to think about it. Put an orientation on it and start labeling the arcs. X1 will be over here, X2 will be here, and now everything's labeled. And here's the game. Don't worry about the orientation on this underarc. Just worry about the orientation of the overarc. And associate to this the following relation. Xi, which you should think of right now as a formal generator. Don't worry about what it means. Plus T, Xj, is Xk, plus Txi. The way I like to think about that is you're moving along here on Xi, and you get down to the crossing, turn left. Then do the mirror image thing over here. Xi, Txj, Xk, Txi. But go ahead and write down the relations that you get from the crossing. From the first one, we'll get X0 plus Tx, X1 is X2 plus Tx0. The second crossing will give you X2 plus Tx0 equals X1 plus Tx2. And the third will give you X1 plus Tx2 equals X0 plus Tx1. And if you fiddle with these two, you can see very quickly that you'll get this one. It's always true that any one relation here is going to be a consequence of the others. So you can pick whichever one you dislike the most and just ignore it. The second thing we're going to do is kill X0. We're just going to ignore a contribution from X0. And by the way, we'll be able to justify this very easily. But right now, I just want to show you how to compute this thing. So now get rid of X0. Where do you see? And now put together a matrix, which will actually be the matrix M in the talked about a moment ago.
Excuse me, why did you split out the x0?
Why do we split the x0? I can explain this, but I would rather hold off on doing it. There's a very cute way to see it that's nice, and I think it's something that's going to come up in Susan's discussion. It's really nice. So
really, normally when you label the arcs, you think of x0, x1, etc. as meridians, but actually in what he's written on the right, you should think of them as elements of a commutator subgroup. And maybe x naught is
x
well,
naught,
not quite.
when you lift the up in the intrinsically cover x naught, sort of like a maximal tree. And by eliminating it, you're collapsing a maximal tree and turning all these x1 and x2s into actual elements of the commutator subgroup, which is what Susan's saying. But
yes,
hold off on that.
Yeah, maybe I'll explain that.
Because right now I just want you to see how easy it is to repeat these things.
Is that related to sort of the marked edge?
I'm not sure what you mean by that.
He means in the Kaufman space,
Oh!
you mark an edge.
No, I don't think so. And by the way, you're free to ignore any of the any generator. It doesn't have to be x0.
Right.
No. I'll tell you, if you keep the x0 in, you compute this thing, you'll get a matrix that isn't square. And if you take GCDs of minors, you're still in good shape. So if you really don't want to do it, don't do it. It's not going to matter. You can leave it in and just take GCDs of minors. But the way I'm doing it, you do have one determinant compute and you go. All right? So yeah. And up at the top, we're going to, up at the top we'll put x1, x2, and then, it's not chalk, is it? And then the relations will go in rows. So for example, here we've got tx1, yeah? x2, but it's on this side, so we've got to bring it over as minus 1. Yeah. And then over here we have a minus x1, so there's a minus 1 here. Of course it's easy for it. And over here it's 1 minus t for x2. Yeah. That's the matrix that describes the homology of the universal Bueling curve for the truffle. And if we take the determinant of this, then you get, well, you notice it's going to be minus t squared plus t minus 1. But we're only interested in this up to units. So let's introduce a symbol here that will be very useful in the future. The dot over means equal to multiplication by unit. And so this is the same as the usual thing. This is the normal way you normalize this. You might make this positive. So anyway, so that's the Alexander Polynomial. If you want to get the higher ones, delta 2 and all the others are trivial. Because if you now take the GCD of the 1 by 1 matrices, obviously you're going to get a unit right away. So the GCD. Okay, so
is that just a fact of, like a consequence of the fact that this is a tiny example, or is there something special about having?
Yeah, if you know what two-bridge knots are,
okay.
it's
So
a consequence of that.
Okay.
Yeah. In fact, you could, not too far from now, I'll explain how you can get this with some other presentation of the group. And in fact, you get a one-related group that gives you a 1 by 1 matrix. And so, literally, all the Spanish. So, if you do this with the figure 8, I'll let you do that. That's probably dull. But the figure 8 is the example, and it gives you t squared minus 3t plus 1 because of time. I'll skip that. Here's a nice example that's very classical. This is, I think this is a Cordless Survey. I think this one's been known for ages. I'm a great person to have to draw this. bad day for this. Sorry. Let me try one more time. Sorry, transparency. I heard Gordon give a talk once, and he drew this one, and he said, this is the other knot. Meaning that this is as far as anybody was willing to do on a blackboard. So this is the knot. By the way, this is the first and only four crossing line knot of the tables. And this is the first and only three crossing knot. And this is in fact the stevedore. And this is 946. And what's remarkable about these examples is that in both cases, delta is 2t squared minus 5t plus 2. And in both cases, the h1 of universal Bueling coverage rational coefficients is cyclic. So it does not see the difference. But the homology with z coefficients does see the difference. And it's difficult to actually understand modules over ZTT inverse. And I mean, it's much easier to work over QTT inverse. And this is a real problem in knot theory, is that this algebra is tough. But in fact, what happens here in the first case is that all the higher Alexander polynomials also can't see the difference. But if you look at E2, this is ETT inverse for 6-1. But if you look at E2 for 946, it's the ideal, and this is easy to check, it's the ideal generated by 2 minus t and 2t minus 4. And the reason that this is not ZTT inverse can be seen by setting t equal to minus 1. If this were TT inverse, then setting t equal to 1 here should give z. But in fact, when you set t equal to 1 here, you get minus 1. You get 3 and minus 3. And so I'm just going to say E2, setting t equal to minus 1, gives 3z, which is not z. So that's why this is not ZTT inverse. So there's a lot of subtlety in the Alexander ideals.
Times the dyadic integers. I think actually E2 should be isomorphic to 3 times the dyadic rationals. Yeah. Because T is multiplication by 2.
Towards the end, sometime in the second week, we're going to talk about some of the dynamics that arises from looking at twisted invariants. And even in the untwisted case, this 2 here causes some very strange behavior in universal Bueling homology when you look at it from a certain angle. There's a solenoid there. So because of that 2, it's showing up a little bit that ideal case as well. So.
Actually, maybe it is 3. Never mind. It might be 3z. Because multiplication by t is multiplication by 2, but it's also multiplication by half. So maybe E2 should be 3z. Whatever. That's an exercise. What is E2 actually? Is it just 3z? I think maybe it is.
All right. So let's see. A couple of other things to mention. The knot you get here by I don't have to take this one to be a mirror image, but I want to. This is a square knot. It's a connected sum. of two trefoils. If you were to compute the Alexander polynomial of a right-hand trefoil and the Alexander polynomial of a left-hand trefoil, it would be very disappointing. Isn't the same. If you were to, by the way, I did not mention the dependence on the orientation. If you used an orientation to make that computation of it, if you reverse the direction of the knot, you'll also find that the Alexander polynomial doesn't change. So these invariants are insensitive to that kind of stuff. And here, of course, this polynomial is the same as this polynomial. And the Alexander polynomial of this knot is, in fact, the product of the two Alexander polynomials. So this is t squared minus t plus 1 squared. But by the way, this is a case where if you want something in this second Alexander polynomial to be non-trivial, you've got it. And this turns out to just be a copy of t squared minus t plus 1. And then the third is trivial. This is not a t originally. So in general, if you take a connected sum, it's a product. Oops. And more general than a connected sum is a satellite. To take a satellite, you take a knot inside a solid tube, and then you knot the tube. So it's two knotting operations. Salvage some of my pride here by drawing something. Okay, there's a great. This is a knotted tube, and inside we'll put a knot, and the knot inside will be a satellite knot. So you can put a knot inside of here. You could make it very simple, or you can make it very complicated. You could put in little local knots. If I just do that and close it up, does anybody know what we get? Just the red knot now. Pardon me?
The connect sum.
Exactly. Yeah. This is why the connect sum is a special case of the satellite construction. Yeah. But we could put something even more complicated in here. And this knot on the outside, is called the companion knot, and often denoted by K, some symbol K hat. The knot inside. Now, if you just take the knot that you put inside and just think of it as a knot, not shake it out. The knot that you put inside the solid torus. This is the well, I shouldn't say shake it out. If you just think about the knot that's that you put into the solid torus. So in other words, undo the black torus and just look at the knot itself. That's a trefoil. This is the companion. I think the language has something to do with actual planets and things. So this is the trefoil.
You put the same word for both.
Did I? Yeah, you're right. Pattern. Sorry, thank you. Pattern. Pattern. So this is also a trefoil here. It could have been anything. And in this example, the pattern is going around once. So the algebraic winding number here, also the geometric winding number is 1. But you could imagine something that goes around 5 times and so on and so on. And then the result is that the Alexander polynomial, the satellite, is the Alexander polynomial of the companion times the Alexander polynomial of the pattern. But you have to evaluate this one instead of a t. This one's evaluated at t, but this one is evaluated at t to the n, where that n is the winding number. Take it to be positive winding number. I mentioned this result because when we come to the twisted invariant, there's a nice problem that might be fun to work on. I don't think there's as far as I know, no result to that. Just the Alexander polynomials of satellite knots. Yeah.
The winding number? To which reference point?
To a reference point
Yes, one number where.
in winding. Well, you could just think about a meridian with saw torus, and just count the number of times you go through with sine, and then just guess at that. Okay. There are a few other properties, and I'll just end with those. Some properties of the classical Alexander polynomial, and again, the reason I want to mention them is because for some of them they fail for the twisted case, and some of them they're open. So there's some nice things to think about here. Number one, a delta of 1 is plus or minus 1. We've already seen that. It's not clear what this is generally for twisted Alexander polynomials. For certain classes, it's not. You'd think something like that would be easy because it's just a homological condition. This is really just telling us basically that that if you sew the meridian back into the knot, you get S3 back. This is a very simple homological statement, but it's not. The analogous thing for twisted Alexander polynomials when we get to it is not. It's not. I mean, it's known that it fails. It's not known what it is generally. Number two, the degree of delta is even, and it's less than or equal to twice the genus of the knot. What is the genus of a knot? It's the minimum genus of a spanning or animal surface. This even bit is going to fail. That's not remarkable at all. So we'll see. Something like this will be. I don't even think this is. I don't even think the call is now. Okay, number 3.
Can I ask you about the other Alexander polynomials before the twisting? Do
Oh,
you have
yeah.
anything similar to this?
Yes, and I should be putting eyes down here.
Oh, okay.
Because they'll also, yes, thank you. That's right. And this one's interesting that we have if you replace t by t inverse, we get the same thing. In other words, the coefficients are palindromic. We saw it here. 1 minus 3 to 1, 1 minus 3 to 1. This condition is known for twisted Alexander polynomials in many cases. And again, I said we got this yet, but in the case of representations that are unitary, a few others, eclectic, symbolic. There are cases where this is done, but it's not true, Jeff. This actually can fail even for representations. SL, and that's so again the complete story there is I'll say another thing. This is a fiber knot, and you notice that the Alexander polynomial is mono. And the degree of this thing is actually twice the genus of the knot. The trefoil bounds a fiber. We'll talk about what fiber knots are later. So right now I'm just trying to say a few things about these properties. Which ones hold classical case and which ones maybe aren't so clear. Twisted case. For fiber knots, you get a monic polynomial. It'll turn out that the monicity continues twisted Alexander polynomials when you have fiber knots. Exactly. Here, it's not a sufficient condition to know that you've got fiber.
Minus what fiber is?
Monicity.
No, can you remind us what it means to be a fiber knot?
I'm sorry?
Can you remind us what
Oh,
it means
yeah,
to be a
yeah,
fiber
sure.
knot?
In fact, I'm at this point kind of riffing, thinking I should end and come back to this stuff. But let me say what a fiber knot is. If you've got a think of the exterior of the knot, and you've got a meridian here. I can certainly map that meridian to a circle, make it go around. So just look at the exterior of the knot and look at a fixed knot, fixed circle of meridian on the boundary of the tubular neighborhood. Okay? I can certainly send out to a circle. There are lots of ways you can extend this map over the exterior, but the knot is fibered. If we can extend this map to a subversion. By subversion, since this is one-dimensional, I just mean that at every point there should be some direction where the tangent vector is not collapsed. So at every point, some direction you're making progress around the circle. But from a topology point of view, this is sort of a geometry definition of it. From a topology point of view, it simply means that the exterior fibers of the circle. So I like this point of view because if every value here is a regular value, then when I take the preimage of any value here, I'm going to get a surface. And as we go around, those surfaces that you're getting preimages of points under the submersion, those surfaces will span out the knot exterior. And so a knot is fibered if there's a whole bunch of surfaces. This is just the knot just coming through here. Here's the knot coming through, here's the meridian. If there's a whole one-parameter family of surfaces that swing around, and the interesting thing is what happens when they come back here. And then you get a non-trivial mapping. In some ways, fiber knots are among the simplest knots. If you think about the fact that the Alexander Polynomial is a characteristic polynomial for the homology of rational coefficients. Okay, so the question is, obviously monic is necessary for fiber knots, but it's not sufficient. But there is a kind of a beefed up version of this for twisted invariance, which provides something that's closer to a necessary and sufficient condition. This is work of Friedel and Ducey, which I'll see a little bit about. So I think I'll stop here. This is the sort of the classical review. I think tomorrow Susan will say something about nice sources of representations, because we need to be able to find knot-group representations without killing ourselves that are interesting, so that we have some stuff to apply when we do the twisting. Then we'll even get to doing the twisted stuff. And I want to show you first the simplest way to compute twisted Alexander polynomials. It's frankly, it's almost as simple as what I did over here. That's what I want to do. Because I like to cut through all the algebra and compute the things and show you how the algebra can shed more light. It'll be very, very concrete.
More questions? Well, thanks again.
What's the schedule?
Yeah, we